In this video, we'll learn some of the common techniques used to algebraically manipulate integrals so that they resemble one of the forms on the standard integral table that's given to us in the HSC exams. The first example is the following. It's the integral of 1 divided by 4x squared plus 9 dx. Now in this integral, we have a constant numerator and the denominator is a quadratic polynomial. But in fact, it's not just a quadratic, it's an irreducible quadratic, which means we can't factorize it into linear factors, or real linear factors is what I should say. Of course, we can factorize it into complex linear factors, but we don't really want to involve complex numbers in integration if possible. We'd like to avoid that. So we have an irreducible quadratic in the denominator. That means that we want to try to complete the square in the denominator. Now, in this case, the square is already completed. It's already done for us, but we just have to factor out the 4 here so that we have x squared with a coefficient of 1. That's going to be very helpful. So if we do that, let's take out a 4 and we're left with the following. X squared plus 9 on 4. Now here we have the form of the tan inverse. Okay, when we integrate this, we're going to get a tan inverse. Now in the integral sheet, it's given as x squared plus a squared in the denominator. So it might be a good idea, just when you're first starting off, to write the constant as something squared. So in this case, 9 on 4 is quite easy because both the numerator and the denominator are perfect squares, are square numbers, right? 3 on 2 all squared gives 9 on 4, so we can just write it like that. Now, obviously when you get more comfortable with these, you don't have to do this step, but this is just maybe if it's your first time seeing how to do these. Okay, so we have 3 on 2 all squared, and then we can go ahead and apply the tan inverse formula. So that's going to be 1 on a, in our case a is 3 on 2, times tan inverse of x divided by a. And then of course plus c. And we can tidy this up a little bit. 1 on 4 times 1 over 3 on 2 is going to be 1 on 6. And this tan inverse will be 2x over 3. And plus our constant. And that's the end of the first question. Now the second question. That's going to be the integral of x divided by 4x squared plus 9 dx. Now you should notice that these look very similar. The only difference is that in the first question we had 1 in the numerator, and in the second question we have an x in the numerator. The denominator is still that same irreducible quadratic 4x squared plus 9. Now, in the second question, we have 4x squared plus 9, which is a degree 2 polynomial in the denominator, and in the numerator we have a degree 1 polynomial. That means that there's going to be some sort of a logarithm popping out in the solution. The reason is because when we differentiate the denominator, that's a degree 2. When we differentiate it, it becomes a degree 1 polynomial, which is exactly what we have on top. Now, the derivative itself isn't exactly on the top, but it's a degree 1. So we can manipulate it in order to get to the derivative of the denominator. Now, if we think about it, what is the denominator's derivative? It's just 8x. So all we have to do is multiply the top by 8. So let's do that. We have an 8x divided by 4x squared plus 9 dx. Now of course we can't just multiply by 8 for nothing, that just changes the value of the integral. So we want to compensate by dividing by 8. And now I can see that the denominator has its derivative in the numerator on top of the fraction. Okay, so we can just go ahead and apply a straight log in this case. So that's going to be 1 on 8 times the log of the denominator, which is 4x squared plus 9. And of course, plus a constant. Okay, and that's the end of the second one. Okay, question 3. We have the following integral. It's the integral of 3 over the square root of 1 minus 5x squared dx. Now, in this example here, we have a constant in the numerator and we have a quadratic in the denominator, except we have the quadratic underneath a square root. Okay, and there's 3 types that we come across in the Extension 2 course. We have the inverse sine, or we have those two logarithm functions, which you can see on the standard integral sheet. Now, how do we know which one it's going to be? Well, if the x squared underneath the square root has a negative coefficient, if the coefficient of x squared is negative, that means it's going to be an inverse sine. Okay, and that's what we have in this case here. So we need to try to manipulate this to look pretty similar to what's in the standard integral table. Now, in the standard integral table, the x squared has a coefficient of 1, or negative 1 I should say. So we want to try to manipulate this, do a bit of algebra, in order to get x squared with a coefficient of 1. And that's not too difficult. So what we're going to do is we're going to factor out a square root of 5. Now, if you can't see why it's going to be that, we'll just do it in 2 steps. And like I said earlier, this is probably something that you can do in 1 step once you become comfortable with it. But just for the first time, we'll do it in 2 steps so you see exactly what's happening. So I want x squared to have a coefficient of 1, or really it's going to be negative 1. Okay, so let's factor out a 5 inside the square root. So doing that, factoring out a 5 from 1 gives me 1 on 5. And from the 5x squared is just going to be x squared. Okay, and then now this 5 here, I can take it outside the square root, and that's where my 1 on root 5 comes from. So if I take it outside the square root, it becomes root 5, and then I just take that outside of the integral. So 1 on root 5 times the integral of 3 over, my pen's playing up, 3 over the square root of 1 on 5 minus x squared dx. Okay, and again, underneath the square root, this 1 on 5 is equivalent to the a squared, which is given in the standard integral table. So what I'm going to do, I'm going to write the 1 on 5 underneath the square root as the square of 1 on root 5. Okay, you'll see, that's a tongue twister. I'm going to write 1 on root 5 all squared, and that gives you 1 on 5 minus x squared dx. Okay, so now I'm really, I can see clearly what form it is, and I can apply it to, the formula to this integral. So this is 1 on root 5, that's just the 1 on root 5 that comes from this bit here, from right here. And now we can apply the rule. So it's going to be times 3 sine inverse of x over a, which is 1 on root 5, plus a constant, slide it up a little, and then just tidying things up, this gives us 3 on root 5 times sine inverse of root 5x plus a constant. Okay, and that's the end of the third example. Okay, for the fourth example now, we have the integral of 1 divided by the square root of x squared plus 2x minus 1 dx. Now, this integral here, we again have a square root with a quadratic underneath it in the denominator. Okay, but the difference between this one and the one before it, in question 3, we had a negative coefficient for x squared. That meant it was going to be inverse sine. But for this one, we have a positive coefficient of x squared. Okay, so that means it's going to be one of the 2 logs that we have in the standard integral. They're the last 2 standard integrals that we're given. So how do we know which one to use? Well, we need to actually complete the square underneath the square root here. So let's go ahead and do that. Now, I think if you're watching this video, you should know how to complete the square. So this is going to be x plus 1 all squared minus 2, okay, dx. So here we have our term, our x term squared minus a constant. Okay, so we look on the standard integral and we use that formula, the one where it's x squared minus a squared. Okay, but this isn't exactly x squared, is it? It's x plus 1 squared. So what we have to do, we have to be a little bit careful. We have to make a u substitution. So we can say let u equal x plus 1, and then we can just differentiate du on dx equals 1, which means that du is equal to dx. Okay, so we can go ahead and make that substitution. So doing that, we get 1 over x plus 1 becomes u, so this is u squared minus 2, and dx becomes du. Okay, now this is going to be in the form that we're given. What we could do, we could write this as the square of root 2 squared, just like we've been doing before, just to see exactly what our a is going to be. But I'm going to say it again, we don't have to do that. That's just for us to see clearly. After a few times, you won't even bother. So let's now evaluate the integral. That's going to be the log of u plus the square root of u squared minus 2. Okay, so actually we didn't even need to do that. I don't know. It's okay. Like we could have just left it as 2 plus c. But this is now given in terms of u, while the question was given in terms of x. So we have to go back and substitute for x. So this is going to be x plus 1 plus the square root of x plus 1 squared minus 2 plus c. And this is perfectly fine. However, underneath the square root in our log, we could rewrite that as x squared plus 2x minus 1. So what we're doing is we're literally just reversing the completing of the square. Okay, and you don't have to do it. I mean, this is still a correct answer, but it's nice to have it in the same form that it was given in the question. So it's going to be the square root of x squared plus 2x minus 1 plus c. Okay, and that's the example 4 done. Alright, now our fifth and last example for this video is this one here. It's going to be e to the x over e to the x plus e to the negative x dx. Now, these types of integrals are interesting because they're not exactly in any form that's given on the standard integral sheet. Okay, but what we can see is that we have a lot of e to the x's and e to the negative x's. They can come in different kinds of styles, but it's all about how we manipulate these. And the trick or a very useful tip in dealing with these fractions of exponentials is to multiply the top and the bottom by either e to the x or e to the minus x. And that's because we get a lot of cancellations. So in this example, we're going to multiply by e to the positive x, so just e to the x. And the reason we do that is because this term here, when we multiply it by e to the x, actually just becomes 1. All right, so there's a nice cancellation there. So let's go ahead and do that and see what we get. So e to the x times e to the x is going to be e to the 2x. And in the denominator, if I multiply all that by e to the x, I get e to the x times e to the x, which is e to the 2x. And then, like we said, we get e to the x times e to the negative x, which gives us just 1 dx. Okay, that's really good, because what I have on the denominator is e to the 2x plus 1. If I differentiate that, I'll get 2 times e to the 2x, and that is almost what I have in the numerator. All I'm missing is that factor of 2. So if I can go ahead and multiply by 2 on the top, I'll get exactly the derivative of the denominator. But of course, like we have seen before, we can't just multiply by a constant for no reason. We have to divide by that same constant. So that means that the net value stays the same. And then now we have an integral where it's a fraction with the denominator having its derivative on top. So that's just going to be log of the denominator, e to the 2x plus 1 plus a constant. Okay, so once again, the tip with these is to try multiplying the top and the bottom by either e to the x or e to the minus x. Okay, and that's the end of question 5 and the end of this video.